Now that we've talked about nuclear reactions in somewhat of an abstract way, by talking about the conservation laws and the plausibility arguments for the reactions happening inside stars and the rates, we can now be a little more specific. I'd like to go over some of the exact nuclear reactions that happen inside stars, for example, and where what that will give us is basically the origins of pretty much all the elements on the periodic table from nuclear fusion. So we can start to go through them. I won't go through every single element, of course, but hopefully we'll see how things progress up in terms of atomic number. Um, a few things to think about at the beginning. I've got listed here. Last time we talked about this energy generation rate. It depends very strongly on the temperature. Another thing that depends strongly on the temperature is the height of the so-called potential barrier. If you remember how we rewrote this a few videos ago, it depends on the charges on the species that come together in fusion, and also on the reduced mass of those two things that come together. And as we go up to heavier and heavier nuclei, this potential barrier height is going to get bigger and bigger. So heavier nuclei have higher Coulomb barriers, so you can only have those reactions when, again, higher temperatures are there. So because of these two things, when we start to talk about what nuclear reactions are possible at a given temperature, usually we're just going to be talking about a subset of them happening at that temperature. Um, if say we're talking about something happening at 1 billion degrees Kelvin, there'll be a certain set of reactions that are right in the sweet spot for that. You can't really fuse uh, nuclei heavier than that because you would need higher temperatures, and pretty much all of the lighter nuclei would have already been fused already because of this strong dependence of epsilon on temperature. So we're going to be, as I say here, imposing a bit of an order on the chaos of all the millions of different reactions that can be happening by talking about, by just sort of looking at what tends to start happening as you slowly march up in temperature and in mass. Okay, I hope that makes sense. Um, well, we can start with hydrogen, right? Again, we've been sort of talking in the abstract. We sort of want to eventually take 4 protons and turn them into a helium nucleus so we can tap that extra energy and power the luminosity of a star. Of course, we know there has to be an intermediate stage of transformation there because a nucleus is not made of 4 protons, it's made of 2 protons and 2 neutrons. So there have to be 2 beta decays in there that turn 2 of those protons into neutrons. And I also mentioned last time that it's probably unlikely to think of a simultaneous reaction where all 4 of these things come together at the same time and then magically turn into one helium. Um, you know, the cores of stars are dense, but they're not that dense. It still is going to be a much more rapid thing to look at pairwise reactions. 2 things coming together, and it's much less likely for more than 2 things to be coming together. Okay. Well, where do we start? If we start with just hydrogen, just protons, and we're really talking about just the nuclei here, not the electrons, right? If we're at temperatures of millions of degrees in the cores of stars, the electrons are stripped away. These are just fully stripped ions and just the bare nuclei flying around. So if all we have is hydrogen, the simplest thing that you could imagine would be 2 protons just sort of slamming together in a strong reaction where they become a helium-2 nucleus. That's a very rare thing, right? It would be just a proton sticking to another proton with no neutrons around, right? The standard form of helium has 2 other neutrons involved, so it's got a mass of 4. This thing is just called a diproton. It still is an isotope of helium, but there are no neutrons. And it essentially doesn't exist. It really just, if you ever to try to make one, it would just immediately break up into 2 protons immediately. I tried looking up the properties of the diproton. thinking of it sort of as an unstable isotope that has a half-life that eventually decays into 2 protons. No, it doesn't even appear in the lists of isotopes. It's so unstable and so unlikely to ever find anywhere in nature. So this might be one of the things we think it might be starting the process, but it's not. It just doesn't happen. The other thing we might think would happen inside stars, and this actually did happen a lot right after the Big Bang, when there were a lot of free protons and free neutrons flying around, would be that a proton slams into a neutron and becomes a deuterium nucleus, right? Again, deuterium is an isotope of hydrogen. The nucleus has 1 proton and 1 neutron, so there's really nothing strange happening here. They're just sticking together to form this nucleus. And there was some fusion happening in the universe right after the Big Bang, and this process was the first step in the chain that started some of those fusion reactions happening. But in stars, we don't have free neutrons flying around, so it's got to be something else. And it wasn't until about 1939 that Hans Bethe realized that the only way to really have this get going was not a strong interaction, but a weak interaction. So in other words, 2 protons come together, they come into close proximity with one another, and right as they're about to start to repel, there's this quantum tunneling, but also right at the same time, there's a weak reaction. One of those 2 protons turns into a neutron and, of course, creates these other decay products of the weak reactions, and the proton and the neutron immediately stick together to form this deuterium nucleus. That might be a multi-step thing that I just talked through, but typically astronomers just talk about it as if it's one single process, because all those different things are happening in a very quantum fuzziness type way, and it's really just one thing that tends to happen. It's a weak reaction. Oh, by the way, one of the other reasons that the weak reactions are called weak and the strong are called strong is also that weak reactions are much less likely to happen. If everything else is on equal footing, strong reactions have much higher rates and much higher cross sections, for example, for happening. So for example, this weak interaction has a cross section that's 10 to the minus 20 times that of the other typical strong reactions that we're going to be talking about for fusion. So it's in fact so weak that this thing has actually never even been created in the laboratory. It's theoretical. We're pretty sure it's actually happening inside stars, but we just haven't been able to reproduce the conditions to make it happen in the lab because it's so infrequent. Okay. Right, and because it's so infrequent that if this is the first step in a chain of multiple things that have to happen to make helium, this is the thing that actually limits the rate. It's the so-called bottleneck, right? You have to really wait a long time for one of these things to happen. Once it happens, then the other things happen rapidly. And we'll look in a second at what those other things are. Well, okay, so now what do we have here? We have lots of protons, and now we have some of this deuterium flying around in the core of the star. And if the core temperature of the star gets to be at least 1,000,000 degrees, it can enable another process, another strong reaction. A proton can basically collide with a deuterium atom and create a nucleus of what we call helium-3. So again, it's a strong reaction, so we're just taking this 1 proton and this deuterium atom, which is a proton and a neutron, and slamming them together to create this nucleus. This new nucleus has 2 protons, so it's an isotope of helium, atomic number 2, and it's got a mass of 3. This helium-3 is an interesting isotope of helium. Sometimes they call it trialphium. I don't know. I've never really heard that too often, but it's an interesting name. People think there's a lot of it, a lot of helium-3 on the moon. So if people ever go back to the moon and try to start self-sustaining industries up there, mining of helium-3 might be one of the most lucrative things to do up there. So, right, so in stars, it can be created just from the simple strong reaction, which happens relatively rapidly once there starts to be deuterium inside the star. Some stars are born with some deuterium, or some objects are born with some deuterium. And in fact, in brown dwarfs, which are objects that are just slightly too low mass to be stars, they can undergo a little bit of fusion using their primordial deuterium that they're born with, and they can burn some of that up into helium-3. It takes a few million years to do that, and they can glow a bit. They can have some luminosity from that, but it doesn't last that long. And like I say here, eventually that initial supply gets used up, and the brown dwarf is too low mass for the temperatures to rise to the level of being able to do anything else with this helium-3. So it just sits there, and the brown dwarf gradually cools off over the next few billions of years. Okay, so, oh yeah, there's other things that can happen. Some systems, even some large gas giant planets, can have lots of deuterium, so they can sometimes undergo double deuterium burning, where two deuteriums slam together. You might think that would be a good channel to make regular helium-2, right? Regular helium-4 also, because one deuterium and another deuterium would be a P and an N, and another P and an N, and that's a helium. But for some reason, this channel doesn't seem to create a lot of helium. Maybe there's too much kinetic energy involved in slamming these two things together, because what tends to happen is one of the say maybe one of the neutrons breaks off and the rest is just P, P, and N, or maybe one of the protons breaks off like that, and the other thing is P and two N's, which is another isotope of hydrogen called tritium. And the tritium is a radioactive element that eventually will decay down to helium-3 also. So yeah, you can't get much regular helium-4 this way, but it can sometimes happen in these brown dwarfs and giant planets. But in stars, what actually happens? The third step is the third thing in the box here, right after the previous page. There's 3 steps, so maybe I should just go back. Right, the first step is this weak interaction where the 2 protons turn into a deuterium. The second one is deuterium burning to create helium-3. The third major step is where now you have a lot of helium-3 flying around. Those 2 helium-3s crash together, and, well, you might think they would create something with an atomic mass of 6, right? 3 things plus 3 things. There are no stable nuclei with an atomic mass of 6. So the next best thing is a helium plus 2 protons that just go flying off. And we can verify that this is a strong reaction and the baryons are conserved, right? A helium-3 would be P, P, and N, plus another P, P, and N. And what does that give us? There are 1, 2, 3, 4 protons involved. 2 of them wind up in the helium nucleus, and the 2 of them go flying off in other directions. There were 2 neutrons. Those end up in the helium nucleus, and everything is conserved. So this is also a strong reaction, so it's also fast. So everybody had to wait for that weak reaction, and then these second 2 happened in close succession. Yeah, so actually this is how something like 85% of all helium atoms in the sun are created. This is called the PP1 reaction chain, proton-proton 1. And in the next video, we'll talk a little bit more about some alternate ways that helium can be created initially out of 4 protons. But again, this is the dominant one happening in our own sun.